Welcome to Cognitive Spirals, exploring the latest research into consciousness, cognition, and machine intelligence. I'm really excited about the topic we have today. It's one we've all been chewing on for a while, isn't it?
Absolutely. It feels like we're on the cusp of some major breakthroughs, and maybe, just maybe, we might even make some headway today, although that's probably wishful thinking, haha.
Hopefully, but I think we might disagree on where those breakthroughs might be, haha. I'm not as optimistic as you are about the current path.
Yeah, I'm with you on that. There's a lot of hype, and it feels like we're missing some fundamental aspects of intelligence in the current mainstream approaches.
So, kicking things off, I recently read this paper on using fMRI data to train neural networks, essentially trying to decode neural activity directly and replicate it within an AI system. It got me thinking, are we finally starting to see the convergence of neuroscience and AI? I mean, we've got this amazing deep learning technology, and we're also gaining more detailed insights into how the brain works. Shouldn't we be combining these two fields more aggressively? Think about the potential for really understanding and then replicating, rather than just approximating. What makes us intelligent?
That's interesting. I think there's definitely value there, but I'm not sure we need to explicitly copy brain activity to achieve artificial general intelligence, AGI. The brain, while obviously capable of intelligence, is still ultimately an evolved, somewhat messy solution. We have the opportunity to be more efficient and even more innovative with the algorithms we develop. Deep learning already shows incredible performance in tasks where our brain struggles. I've been really looking into the latest work on transformers and their capacity for generalization. It's pretty mind-blowing.
Hold on a second. Transformers are amazing at pattern matching, yes, but are they really reasoning? We see all these impressive outputs, but is it genuinely understanding? It's like, a really good parrot. We're feeding it tons of data and it's regurgitating, and it's doing it very convincingly, but I just don't see the leap to actual intelligence. I think our current deep learning methods are a bit too statistical and lack the kind of symbolic manipulation that seems essential for higher level cognitive functions. We need neuro-symbolic approaches, something that combines the pattern recognition of deep learning with the logical reasoning capabilities of symbolic systems. I think that's where the goal lies.
I agree with you to an extent. I'm concerned that we're treating intelligence as if it's just about finding complex patterns in large data sets and then doing a transformation. Think about how we learn as kids. It's so much more about our body, how we interact with the world over time. Seeing something move, understanding its trajectory, understanding how that relates to other objects in the world. Space and time. I think we need algorithms that understand spatiotemporal relationships inherently, and not just as a side effect of learning a huge data set of static images. Deep learning is brute force in comparison. We need a core algorithm that fundamentally understands how things unfold over space and time, and even translate between different coordinate systems.
Okay. So we have some differing viewpoints, which is great for a healthy discussion. I do think, though, that these issues aren't mutually exclusive. Right? So, while I agree that pattern matching alone is not enough for human-level intelligence, I think neuroscience can give us clues on what's really going on. I think decoding the neural activity associated with reasoning, for instance, it's really fascinating and could inspire more sophisticated architectures and training techniques. We are discovering that the brain is not just a static pattern matching machine, but also a dynamic system, constantly updating its representations. The research in things like neuromorphic computing, that's so exciting. These architectures are inspired by the brain's structure. They are event-based, asynchronous, and might be more suited for modeling higher cognitive functions.
But what about the scale, though? The sheer amount of data and compute you need to even come close to replicating, or even abstracting, the kind of complexity we see in the brain. I think that's what we're hitting here with the neuro-symbolic and spatiotemporal approaches. The brain has these incredible, complex, and sometimes weirdly evolved structures, and we're never going to copy the detail. We've seen that deep learning models, especially large language models and diffusion models, show an emergent ability that was not explicitly programmed in. We have got to double down on these areas. The scaling of these networks seems to be driving the emergence of novel properties, and that's where we will see AGI. I think we need to focus on how to improve those generalization capabilities and efficiency.
But that's the whole point, isn't it? I am saying that the emergent behavior that you're seeing is not the same thing as real intelligence. I understand that large language models can generate text and even write pretty decent code, but it doesn't have real-world understanding. They aren't actually reasoning about the underlying concepts and can't form proper causal relationships. It doesn't have the common sense reasoning that even a toddler has. I think we are at a local minima here. I really think that neurosymbolic approaches offer a way out of this plateau. We need to inject more structure into our models and integrate explicit symbolic manipulation and knowledge representations. This can help with causal reasoning and knowledge generalization, which deep learning struggles with so much.
Yes, and it links back to what I was saying about spatiotemporal understanding. The ability to reason about the world is so dependent on an inherent understanding of how things change over time and across space. Think about how a baby learns to reach for a toy. It's not just about recognizing the shape and color. It's also about understanding how that toy moves in relation to its own body, the coordination, the intention. That's spatiotemporal understanding right there. I'm not saying that we need to completely disregard deep learning. It can be used as a great component within a larger architecture. But I do believe that the core fundamental algorithm must include a spatiotemporal component, in that it fundamentally understands it. And we need it in order to achieve a general intelligence capable of moving beyond pattern matching, moving beyond just processing text or images. We're stuck at high-level approximation. The core algorithm needs to be able to translate between multiple coordinate system representations.
Right. So let's unpack that a little bit. I think it's interesting that we're talking about different levels of abstraction. You're saying that neuro-symbolic approaches are needed to bridge the gap between pattern matching and true reasoning, and that spatiotemporal understanding is essential for a more grounded intelligence. I agree completely, but I also think that neuroscience research is important for informing all of these approaches. You see, the brain is the ultimate proof of concept. We have to use our knowledge of how it works to guide our engineering efforts. I'm not suggesting that we have to build a neural network that looks like a human brain, but it is going to give us huge insights into how an intelligent system works. I'm really excited about research that combines fMRI or EEG, or even single-cell recording, with AI to extract the core algorithms and representational strategies of the brain. Things like reverse engineering cortical microcircuits, using AI to analyze and simulate that detail. These insights will be crucial for developing not just symbolic systems, but also for understanding what those symbols represent in terms of their relation to the real world, and also understanding how the brain translates those symbols into actions. We don't need to literally copy the brain's messy hardware, but we do need to be inspired by how it works on a functional level.
But isn't that putting too much emphasis on the biological aspect of intelligence? I think there's no reason to think that human brains are the optimal solution. They are just one solution among many. Deep learning provides a framework where you can start with very simple structures and then scale them up to see what emerges. And it's clear that we are not at the limit of those scaling laws. I mean, think of the progress we've seen in just the past few years with models like GPT-3 or Stable Diffusion. These things weren't conceivable a few years ago. If we just put all our efforts in more neuro-inspired approaches, we might be missing out on other more powerful or more efficient solutions. We should be pushing the boundaries of what is possible with existing tools first, before trying to literally copy the brain. We can learn the general principles without doing 11 copy. I really believe that if we push forward with better data sets, better training techniques, and more compute, we are going to eventually reach AGI with deep learning. Maybe not tomorrow, but it is on the horizon, and I think it's far closer than the other alternative approaches.
But the question still remains, are these models actually understanding, or are they just getting really good at predicting patterns and data sets? I mean, you could even argue that the emergence you're talking about is just the models learning really sophisticated statistical correlations. It's not the same as genuine understanding or reasoning. You see, a toddler can reason about simple cause and effect, like if I drop this ball, it will fall on the floor. This ability is based on an inherent understanding of the underlying physical laws of the world, which current deep learning algorithms lack entirely. And you can't just get that from massive data sets. You need to build it into the model's architecture, and you need to be able to explicitly represent this knowledge. I mean, that's why I believe that neuro-symbolic approaches will ultimately be more effective at building truly intelligent systems. These systems can combine the strengths of neural networks for pattern recognition with the strengths of symbolic systems for logical reasoning, knowledge representation, and causal inference.
Yes, and all that is in relation to something in a coordinate frame of reference and also how that changes over time. I'm with you on that. I think deep learning is a great tool for certain things. It's great at identifying complex patterns and learning from data, but it isn't how we think and how we develop intelligence. It's a means to an end and not a solution itself. I think it's a mistake to believe we can get to general intelligence by making neural networks bigger. I suspect we are very close to the plateau of improvement with scaling. I really do believe that our core algorithmic approach must be able to translate between different coordinate systems of representation, including egocentric and allocentric. Consider how we navigate the world. We constantly update our own positional representation based on changes in the external environment and our interaction with it. That's a continuous spatiotemporal process that we can't ignore. If we are really wanting to achieve AGI, we have to build that into the fundamental architecture of our AI systems. Think about the hippocampus and its role in mapping space. We can learn a lot from such biological structures, but we shouldn't think we can just copy them. We have to understand the fundamental principles and then build them into our AI in a way that is suited to a computer. Deep learning is just brute force in comparison, and will never be able to achieve generalization without huge and continued compute resources.
I think that's interesting, but that predictive framework is, in my opinion, just another way of saying optimization of a model. It's just a sophisticated way of pattern matching. I'm not disputing that the brain has all sorts of predictive elements, but this is happening at a micro level across many layers of the system, and it's that scaling of the system, that emergent property which is so difficult to emulate. I also think that the neuro-symbolic approaches you are all arguing for could get stuck with the same problems in that if you aren't learning the representations, you are just coding them, and the coding is not flexible, it won't generalize, so it can't adapt to different situations. So, I feel like if you try and pre-program everything, we might miss some emergent phenomenon. If you think about the way evolution works, you can't plan everything from the beginning. The details emerge from trial and error and gradual adaptation. I think scaling up deep learning architectures provides a path to discovering these emergent properties. By giving these algorithms the ability to learn their own representations, rather than coding them, allows them a degree of flexibility and adaptability which I think you're missing. We shouldn't try to replicate the brain directly, but instead, we should be inspired by its success and continue exploring deep learning methods. I mean, we don't have to copy the messy biological details. We can focus on what is functionally important. I think we might be underestimating how far we can get with this scaling approach.
I think you're missing my main point about abstraction. The issue with deep learning is that it's too low level. It's learning from pixel data or word embeddings. It's not learning concepts. We know that the human brain doesn't operate at that level. We operate at the level of ideas, categories, and relationships. Think about language. The structure of language allows us to form abstractions, to combine concepts, to reason about things that are not directly in front of us. Deep learning algorithms struggle with this kind of abstracted thinking. You'll find that they also struggle with zero-shot learning. They can't generalize outside the bounds of their training data. And I'm not saying we have to explicitly program in every bit of knowledge. I am saying that our models need a mechanism to construct explicit knowledge representations and also to perform logical reasoning and causal inferences. I think this is why we should invest in neuro-symbolic systems as a route forward. I also think we should really be pushing forward with knowledge graph research. The ability to represent and reason with knowledge, I believe, is absolutely crucial to achieving general intelligence.
So it seems that we've all got slightly different ideas on the most promising path forward. I agree with the points about abstraction, that deep learning needs a higher level conceptual understanding, and also the point that we need a core algorithm that understands spatiotemporal relations. But I also think that neuroscience provides us with the necessary clues, and we shouldn't disregard the potential here. Maybe what we need is a framework that is inspired by neuroscience, which is then implemented with neuro-symbolic logic, and that is also capable of spatiotemporal reasoning. We are very close to an overlap now, I think. What we need to do is focus our research on combining these areas. I think we should push research into using neuroscience data to inform our model designs, maybe using fMRI data for encoding of reasoning, or using EEG data to identify core neural algorithms. I think we should also combine that with research into neuro-symbolic representations of knowledge. And we need to explore the potential of these systems to represent and reason about spatiotemporal relations. I'm really pushing for a combination of all three.
I'm really concerned that we are going down a dead end if we focus purely on deep learning scaling. I think it is leading us down a dead end. I just don't think we will achieve human-level intelligence by scaling those methods alone. My view is that we should really prioritize research into neuro-symbolic models. We should look at ways of integrating structured knowledge representations with the power of neural networks. I think we should be researching the use of knowledge graphs for knowledge representation and reasoning. We should also really be pushing forward with methods for learning structured representations from raw sensory data, and also we need to push forward with the explainability of these systems. I'd like to see more research into ways of combining deductive and inductive reasoning to get to a more general approach. We need to be able to model causal relationships, and we need to understand how those causal relationships might change over time. So I think that we should be really pushing for a combination of neuro-symbolic logic and also the potential for creating explainable and transparent systems. I'm still a massive believer in this kind of approach. I think it's the key to AGI.
And I still think that we need to really focus on spatiotemporal reasoning. I know I'm a broken record here. I think we need to focus research on algorithms that can learn to represent and reason about changes in the environment over time, and also how those changes relate to an internal coordinate frame of reference. I think we should explore more biologically inspired architectures, specifically how the brain represents and reason about changes in position and orientation in space. I think it would be great to explore methods for integrating egocentric and allocentric representations. We also need to consider how these systems can deal with occlusions and also with partial information. And I think we should be really pushing for the development of core algorithms that can translate between different coordinate systems of representation. I think we need to move beyond the feed-forward nature of current AI and think more about how an embodied agent learns to interact with the world over time, and that I think is crucial to AGI. I am really passionate about this approach. I just think it's fundamental to how our intelligence works.
Well, it seems like we've covered a lot of ground today, and we have some clear paths forward in all of those areas of research. I think it is also really encouraging that there is so much interesting research happening, and I think we are on the precipice of some major breakthroughs. It's been great to get everyone's unique perspectives on this really fascinating topic. It's clear that we've got some differing viewpoints, but also a very healthy dialogue about the future of AGI.
Yeah, definitely. It's always good to challenge each other and really think about all the possible avenues, even if we disagree on which is the best one. I think we all agree that the future is definitely bright.
Absolutely. It's a very exciting area, and I'm looking forward to seeing how it all unfolds, and I'm really interested to see how the different approaches that we've all been advocating today will actually work in practice.
Agreed. This has been really helpful, and I'm genuinely excited to see what the future holds. And I'm very interested to continue this conversation again next time.